So we are now in part 2 of chapter 34, which is geometric optics. So we're now going to discuss the thin lenses. Okay. The most familiar and widely used optical devices are called the lens or the lenses. A lens is an optical system of two refracting surfaces. It's like this one. Natay converging lenses like this na siya yung mga two spherical like this surface close enough together that we can ignore distance between them. Okay. So in the double convex, you have two spherical surfaces, and the double concave, you have this two spherical surfaces only. They are separated by negligible distance that we can ignore. We call this one a thin lens because the distance between them is thin. So one of the example of this is what we call this one, the eyeglasses. So if you're familiar with the eyeglasses used to correct your eyesight, or that one. So we will analyze that one later in our video. Let's just focus first on the thin lenses. So one of the properties of a lens is that if you have a light rays that is passing through that lens, which is parallel to the optic axis. So what happens is that in the other side, it will converge as the point at which the incoming parallel rays converge, it will converge at the second focus, F2. Okay. So if you recall, if this is your spherical, what we call this one, surface, that one, if this is your spherical surface, so it has a radius R2, okay, and the R over 2 is the focus. So this one also, if this is this is also your spherical surface 1, it has a radius R some here, and it has focus R over 2 with the distance F. Okay. So the focal length measured from lens center, from the lens center, this is measured. So always have the same, always the same on both sides of the lens. So these focus are the same. So for the converging lens, so the focus are positive for convergent. So we call this one actually positive converging lens. Converging lens. Okay, if the rays diverging from this point emerge from the lens parallel to the axis. Okay, if you have rays emerging from this point, it will emerge from the lens parallel to the optical axis. This one. Okay, a distance F. So if you derive the relationship of the object image for a thin lens, so for example, we have an object here, extended object, the segment PQ. Okay, if you focus on the triangle P, Q, and O, and the triangle O, P prime, and Q prime, these triangles are similar. So since they are similar, so the ratio of the y over s is actually equal to since this is below the optical axis, this is equal to negative y prime over s prime. So this implies that the y prime over y, so negative s prime s. This is actually we call this the magnification for thin lens is equal to m. So another triangle here that are similar is, if you look at the triangle AOF2 and 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 QPF2, this triangle also are similar. Okay, the ratio of y, so here the y over f is equal to the negative y prime over s prime minus f. So this distance here over this y prime. Okay, we have here the negative. So this implies that this is equal to um, uh, y prime over y equal to negative s prime minus f over f. Okay, so if we equate these two, we have actually here uh, negative s over s is equal to negative s prime. So we have s prime over s prime minus, I'm gonna put it this way, negative s prime minus f over f. Okay, so it looks like this. So negative s prime over f plus 1. So if we actually multiply this 1 by 1 over s prime, it will become negative 1 over s minus 1 over f plus 1 over s prime. Okay. So if you put that one to the other side and this one to the other side, so we will have 1 over s plus 1 over s prime. So this is the 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 object's distance plus the 1 over the image distance is equal to the 1 over f, the focus, the object image relationship for the thin lens. Of course, we have this, the magnification for thin lens. Okay. For a diverging lens, those equations that we derived a while ago also applies. So for a converging lens, okay, we have the uh, we have f1 and we have f2. So the point from which the parallel incident rays appear to diverge. So if you so this f2 is the point where the parallel incident rays appear to diverge. So if you have also this one, the first focal point rays converging on this point emerge from the lens parallel to the axis. Okay, so f1. So again, there are many types of lenses. We have here the converging lens. We have this, the meniscus, the plano-convex, converging lens, the double convex, the meniscus, the plano-concave, the double concave lenses. So these are the type of lenses. Okay, how about we derive what we call the lens maker equation. Okay, so can we derive the relationship between can we derive the lens maker equation? So say for example, we have an object. So say for example, we have an object here. Okay, we have the two radius and we have the because we have two surfaces here with radius r1 with c1 and c2. Okay, the first because of this, this one produces an image at point PQ, and we treat this image, the image of the first the first surface to be the image for the object for the second surface. This one also, because of the second surface produce an image q double prime. So from this, what we call this one, this object, this will be the object of this image. This is the object of this image, and this one we treat this one as the image, the object for this second image here. So what do we get from here? So we get actually here that the since we treat this one as our we we treat this one as our the second now this one now is our the object's distance s2 for the second r2 for the r2. So what we have is that s prime s1 prime here is equal to the negative of s2. So why this negative? Because s2 is negative because it's in s2 now is in the opposite side of the incoming rays. If we look at the the rules, here are rules here. The rule number one, here is the rule number one here. When an object is the same side of reflecting or refracting surface as the incoming light, the object distance is positive. So since since the so we treat this one is as our object now, muna man itong object karon. Dili man it's not on the same side as the incoming light. So this is negative and it's equal to S1 prime. So that's what we get here. Okay. So from the the formula of the refracting surfaces. So we have NA, NB, and NC. So the formula is spherical for the refracting spherical surfaces. For the surface one, NA to NB. So this is the formula, R1. And if you are from surface 2 to surface 3, so we have here the surface B to surface C. So we have NB over S2 now plus NC over S2 prime over R2. Okay. So if we apply that, if we apply here that this one, this S2 prime, this is just equal. This is equal to S1 prime. So what do we get here? Sa man nato makuha ni. So this will become NB over negative S1 prime plus NC over S2 prime. NC minus NB over R2. Okay, we have R2. So from that, we can equate, we treat this one Na, since this is an air, so Na is equal to Nc is equal to 1, and we treat that Nb is just equal to N. I mean N. Okay. So we have here, what will happen to this equation? 1 over S1 plus N over S prime 1 is equal to N minus 1 over R1. The other side would be N over negative S1 prime plus 1 over S2 is equal to 1 minus N over R2. We add these two equations. So this is the equation now. If we add this equation, what will happen? So if we add this equation, we gonna cancel this one, and we are left with 1 over S1 plus 1 over S prime 2 is equal to n minus 1 1 minus R1 plus 1 over y minus uh, okay, so we have here okay. Okay, so we have here 1 over S1 plus 1 over S prime 2 is equal to n minus 1 over R1 plus 1 over n over R2. Okay, what can we do? Can we make this one a negative? So we can make this one so negative n minus 1 over R1. R2 will become is equal to 1 over R2. Okay. So what will happen is that it will become 1 over S1 plus 1 over the position of this second image, n minus 1, and instead of 1 over R2. Mag-cover niyo mga Facebook. So the relationship, since previously we derived that 1 over S1 plus 1 over so since we treat the length as a single unit, so we can equate this one as just equal to this one. Okay, so S prime will become, so previously we derived this one F, so this will become now n minus 1 1 over R1 plus 1 over R2. Okay, so this is what we call the lens maker's equation used to determine the focal length from the radii. So here we have the focal length. We have n. This is the index of refraction of the lens material, the radius of the curvature for the first surface, the second radius of the curvature of the second surface, and so on. We call this one the lens maker's equation. Okay. So suppose the absolute values of the radii of the curvature of the lens surface in figure 34.35, this is the figure, both equal to 10 centimeter, and the index of refraction of the glass is n 1.8. What is the focal length f for of the lens? So we suppose that the f here is r positive. Okay. So so if this is our first, this is our okay, this is our first surface. So it has a radius. This is the radius r1, and here it has a radius r2. Okay. So from the, if we look at the rules, let's look at the rules. So the sine rules, negative ang imong r, a positive yung r if the center of the curvature is the same side as the outgoing. The same side as the outgoing. Okay. So the center of the curvature here is the same side as the outgoing. What this is the outgoing light. So the radius of curvature for C1 is positive. This one is positive. But here, the R2 is negative because it is the radius of the curvature is in the opposite side of the outgoing light. So R2 is equal to negative 10 centimeter. Okay. So what should we do next? Okay, let's do the lens maker's equation. 1 over S plus 1 over S prime. This is equal to 1 over F, or this is equal to N minus 1, 1 over R1 plus 1 over R2. R1 minus R2. So, okay. So, basically, this is minus R1 minus R2. So, minus R2. Okay. So, what do we have next? So, solve for, what is F? Solve for this. Okay. So, 1 over F is just equal to N minus 1, which is 1.52 minus 1 times 1 over R1, which is 10 centimeters, plus 1 of minus negative 10 centimeter. So if you have this one, okay. So 1 over F equal to 1.32. So F here is equal to 1.32 centimeter. I mean 1.32. maybe we're gonna use this. So we're gonna use this na lang equation, mas simpler like this. F is equal to -1. Okay, the inverse. Okay, so we have 9.6. Hmm. Sa kwanta no? Okay, so uh, I have something to do, so let's go back. F is equal 9.62, or in one significant figure, this is just 1.6. So in 1.62 centimeter. So the focus here, so you can locate maybe at the center is, so if we have the focus for this one, the F here is equal to the positive 9.62 centimeter. Okay, in B, let's look at letter B. Suppose the lens in figure 34.31 also has n is equal to 1.52 and the absolute values of the radii of the curvature of its lens. Surfaces are both equal to 10 centimeter. Okay, here we're dealing now with the converging convex lens. We call this the double convex. Okay, so let's draw the double convex like this. Okay, so 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 for example, this is our C1 and this is our C2, and it has a radius from this one R1 and this radius R2. This is the incoming light, and at, at F2, okay, incoming light, this is the outgoing light. Okay, so if the center of the curvature is this on the same side as the outgoing light, so therefore R1 here is positive 10 centimeter. Maybe uh, sorry. So maybe let's treat this first as R1 and the second as R2. Okay, this is R1. So the first surface is R1. So meaning the second surface is R2. So this would be R1. How about this one? The first surface R1 and the second surface is R2. So let's check this one. This is R2. The first surface na to is R1. Second surface na to is R2. So correct na. Okay. So sa convex lens, okay. So the first surface na to is R1 and the second surface is R2. Okay. So here is what this is now the C2 and this is C1. And okay. So here na diri ang F na to, F1, F2, and the distance here is F. So from the rule, it says that if the first surface R1, the second surface R2, it the rule says that the if the if the center of the curvature of that surface is on the same side as the outgoing light, therefore it's positive, otherwise negative. So it means that this is now R1 and this is now R2. R1 now here is negative 10 centimeter, and R2 here is on the same side. This is positive. So to answer the questions, we need the equation 1 over F is equal to n minus 1, okay, times 1 over R1 plus minus 1 over R2. Or you can say F is just equal to n minus 1, 1 over R1 minus 1 over R2 to the negative 1. Okay, F n minus 1, 1.52 minus 1, 1 over negative minus 1 over 10 centimeter to the negative 1. So we have so we have here the 9.6. The focus is 9.6 centimeter. In here, 9 is positive for the uh, con converging lens and negative for the con convex lens. Convex lens. Okay. So the first surface is the R1. Okay, this is the first surface na to. So this is the first surface, the second surface. Okay. This is number 1 surface. It has a radius R1. Okay. This is a second surface na to. It's a radius R2. For the convex mirror, like this. So this is the first surface na to. And the second surfaces. Ang first surface na to, it has a radius here, R1. Okay. It's like this one. This is the C1. And this is the R. The second na to is R2 or C2. So that's why that's the orientation. Okay, we can see here. So this is actually negative 9.6 centimeter. So we can see here that for the F for convex mirror is negative. That's why it's called negative lens. And the focus for the convex mirror is positive. That's why it's called the positive lens. So aside from those calculations, we can also get the position and the position as well as the magnification using the what we call this one graphical method. Okay, so for a converging lens, so this is what you are going, this is the, we have a three principal rays. Okay, the first ray is that, so you drew this one, draw, so it's best that you use the protractor. You can also use ruler for this. Okay, so for an object with a length PQ, so you draw from point Q a ray which is parallel to the axis, pass through the second parallel incident rays, and pass through the second focal point F2. Okay, ano siya. And the third one, the second one is the ray through the center of the lens does not deviate. Okay, dira padulong dira. The third one is that from the focus F1, the ray through the first focal point F1 emerges parallel to the axis. The third one is for the diverging lens. So the double convex, double concave, double convex. So we have a, parallel incident ray appears after refraction to have come from the focal point F2. So ngano ganing F2 ni diri F1? Why is it F1 here? Is this F2? Because this is our sumurag. So okay, so F1 here. So 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 in the calculations we based on the what we call this one, the first surface and the second surface. But in a graphical method, okay, so we treat this one as F2 here for the diverging lens and F1 here for the converging lens. Okay, the second ray is the through the center lens does not deviate appreciably. Okay, this one to this one. The ray aimed at the first focal point F1 emerges parallel to the axis. Okay, aim, this is the two. Aim to F1 and emerges to the parallel to the axis. Okay, so this is the graphical method. So for example, we have this. So although, so the best thing to do here is to what we call this one, use graphical method. You can also confirm this using calculations, your answer. Let's just answer letter A. Suppose you have use ray diagrams to find the image position, the magnification for an object at each of the following distances from a converging lens with a focal point. Okay, so you draw a straight line, draw mo dira o converging lens. So so for example, man ang atong image, distance Q and P. So what is the 50 centimeter? So use a radar to find the image position and the magnification for an object at each of the following distances. Okay. So mga distance, this is first is 50 meters. Okay. So first is you make a ray, okay, that is parallel to the axis. Okay. And if you have the focal, it's 20 meters. So maybe this side 20 centimeter. Okay. F2. This is F1. So that is the first. And the second is this one. Must be in the center again. So that one. And the third one, so padulong siya sa F1. F1 and so this na-converge din siya the straight F1. Then it converge. Okay. At some point, both of them will will intersect at this point. So this is the Q prime and this is the P prime. Okay. So then you measure this one. You measure the distance of this using your uh, what we call this one ruler. You measure the distance of that one. Compared it with the computations. This is how you draw the graphical method. You just follow these three methods. Okay. So the important thing is that you know the focus and the position of the object. This is the position of the object. So you can also find the this one, the magnification. You can check the magnification using graphical, but using calculations, of course, you can also do calculations to find the object's position. Okay, for the position, say for example, 1 over s plus 1 over s prime plus the 1 over f. So to find the position, so 1 over s prime is equal to 1 over f minus 1 over s. So implies that s prime is equal to 1 over the focus, which is 20 centimeter. So this is positive because this is converging lens plus minus 1 over the position, which is 50 to the power of negative 1. So we do this. So you will get the position is actually so it's in the positive side. Okay, it is the same side as the outgoing rays. So that's positive. So you try if you measure this one using your ruler, so make sure that uh your your computational and graphical would agree and have small errors only. You measure also the height and find the m, which is equal to negative s prime over s. Here we have negative 33.3 centimeter over 50 centimeters. So you will have negative 3/2 is equal to y prime over y. That's the ratio of the. So you can get the height. If you know this height, you can get this height using this lateral magnification. So you do a graphical method of this. So make sure that your graphical method agrees with the computational method or the analytical method. You try also the B, C, D. So check what happens to the position. So if you put the image of to a different positions, just like this, let me show you this one. So the image are put at different positions. So this is what happened to the images. Okay. So you read about this. So let's answer another problem, which is 34.10. So a beam of parallel rays spread out after passing through a thin diverging lens, as if the rays all came from a point 20.0 centimeter from the center of the lens. Okay. Ang atong basihanan ni is this one, kani the graphical method. Let's base our answer in this graph. You want to use the lens to form an erect virtual image that is 1/3 the height of an object. Where should the object be placed? Where will the image be? Draw a principal ray diagram. Okay, so since we already draw a principal diagram, so this is what the image looks like. Okay, from the first question, where should the object be placed? So from the graphical method, you should be able to to find this one, but using computational method, is equal to 1 over is equal to 1 over f. So the focus here is 20 centimeter. Both are negative 20 centimeter. Since this is a diverging lens. So to find the object's distance, so 1 over s prime is equal to 1 over f minus 1 over s implies that s prime is equal to 1 over f, which is 22, negative 20.0 centimeter. Why is negative? Because it's converging. It's a diverging lens. Minus 1 over s. So the problem is we have two unknowns. We don't know the s. So, but we have here the virtual image that is one. You want to use the lens. Okay, we have here the given ratio. States that the ratio of this. So it means that Rm is equal to 1 over 3. 1/3, this is from our equation, negative s prime over s. So we can note this one as s is equal to 3 times negative 3s1 s prime. Or 1/3. Can we cross multiply this? So s is equal to negative 3 s prime. We insert this result into the equation, solve for the distance. So how did we get this one? It says here in the book that S prime is equal to negative S over 3. Hmm? S over 3? How? S prime. So how did we come here? Because in my calculation, it's this. Positive 1/3 is equal to S prime over this one. Cross multiply. Should be that. So 1 over S is S over 3. So S over 3. What should be this? What should be the image distance? This is S. Okay. So S, this one. So here, so S is equal to negative 3S from this equation. So we divide both sides by 3. So this is what happened. So instead of using this one, so 1 over S plus 1 over negative S over 3. This is equal to 1 over F. So it implies that 1 over S plus or minus 3 over S is equal to 1 over F. So this will become negative 2 over S is equal to 1 over F. So what can we do about here? So unsa man ganatong ipangita? So we want to find where should we put the object? So this is our target variable. So S is just equal to negative 2F. So we have negative 2 times, this is negative. So the object here S is equal to positive 40.0 centimeter. Okay, where will the image be? So where will the image be? Okay, for the image, you're gonna use this one. So this is equal to now to 40.0 centimeter. Okay, if you do our calculations, the image will be should be negative 20 plus 1 over 40. Where should the image be? So maybe we're gonna use this one equation, of course. The image is, I'm gonna erase this one. Just gonna, the image S prime is just equal to negative 40 centimeter over 3. So we get this one. S is equal to 40 centimeter. So negative 13.3 meter. So this is the location. Okay. Then you draw a principal diagram. So your answer must be like this. You draw a principal diagram. So use ruler, graphing paper, and you draw that one. So try. So you can try. So your answer must be like this. You can also find the in your in your diagram, you can find this height of this two. So that's all for our chapter 34. So see you in the exam.